In this video, we're going to do application of the gravity formula. This is an important problem to make sure you understand, okay? So H here is equal to negative 1/2 G multiplied by the time squared plus V naught T plus H naught, okay? Now, for our application problems, G represents the gravity, and depending on the context of the problem, if it's in meters, okay, gravity is going to be represented by 9.8 meters per second squared. And if it's in feet, so if the context of the problem it's in feet, then it's going to be represented as 32 feet per second squared. Okay? So these two numbers you need to write down and have with you as you go through the problem. Our problem down here looks like we're using meters, so we're going to be using this 9.8 for our G. Okay? So G stands for gravity. Now H, what is H? What does that represent? H represents the height of the object at time t. Okay, the height of the object at time t. So t is represented as time. Okay. So the initial height h, this is the height of object at time 0. T equal to 0. This is the initial height. That's what that represents. It's the initial height. Okay. Now this V naught here, this is the height. This is the velocity at t equal to 0. This is the initial velocity. Okay. That sub-zero, that V naught, H naught, that sub-zero there, that's the time equal to 0. Okay. Right when we start, right when we let go of the ball, the initial speed, whatever it is, okay? So time is in the units, whether it's hours, minutes, seconds. It's here, it's seconds, and the distance, meters here, okay? So what are we going to do here? We're going to take this formula, and we're going to try to solve this problem here, okay? So a rock is thrown upwards, all right, upwards, with a velocity of 20 meters per second, okay, from the top of a 24-meter high cliff, and it misses the cliff on the way back down, okay? The question is, when will the rock be 7 meters from the ground? All right, so anytime we're working a word problem, we want to look for what the actual question is. If we know what we're looking for, that's going to really help us out in figuring out what in the world it is, okay? So when will the rock be 7 meters? That's when is time. So we're trying to find t, okay? That's what we're looking for is t, okay? So here's our formula. H equals negative 1/2 G T squared plus V naught T plus H naught. Okay, so first thing I do when I go through a word problem is I look at all the numbers. So the first number I see is 20. So velocity, so the ball is thrown upwards with a velocity 20 meters per second. So let's draw a picture because we got this dude on a hill, okay? So this dude's on a hill, and they're going to throw the rock. Now the rock is going to fly like this, right? In a parabolic fashion, okay? That's not his head, that's the rock, right? Okay. Yeah, there we go. All right. So we're throwing the rock this way. Now, what do we know? Okay, the initial velocity, the rock is thrown upwards with a velocity of 20 meters per second. So we're throwing up at 20 meters per second. That's my initial velocity. So this gets replaced with 20. Okay. Now, what else can I replace? Well, the next number I see is 24. So we're throwing from the top of a 24-meter cliff, okay? So let's assume that, we've got our 24-meter cliff. Okay, let's not account for the height of this person. So this whole distance here, 24 meters, okay? Because we don't know how tall the person is, so we're not going to get into that, all right? So 24 meters from my height. So my starting height at time 0 is going to be 24, okay? So that takes care of that number. The next number, okay, it says it misses the cliff on the way down. That's how I know that it's coming down this way. Now the next thing is, when will the rock be 7 meters from the ground level? So 7 meters from the ground level. Do we want the rock to hit the ground? No, we want to be 7 meters from the ground level. So we want to know, when is the rock right here? Okay? So how do we know what that is? Is that time t? Is that gravity? No. What is that? That's the height of the object at time t. We want that to equal 7. Okay, and then my gravity here, it's either going to be 9.8 or 32. Which one is it? Since the context is in meters, I use the 9.8. So my formula becomes 7 equals negative 1/2 and then 9.8 t squared plus 20t plus 24. Okay, so I type that in. This is going to get me negative 4.9 t squared plus 20t plus 24 equals 7. To use the quadratic formula, I need to have a positive. I need to have it equal to 0. Neither one of those are true right now. Right now, my a is negative and it's not equal to 0. Okay, so to fix this, I'm going to move the 7 over here. So I have 0 equals negative 4.9 t squared plus 20t plus, and then I guess that's 17. Now, a is not positive yet, but how do I make it positive? I'm going to multiply everything by negative 1. And so that's 0 equals 4.9 t squared minus 20t minus 17. And now I can use the quadratic formula with a equal to 4.9, b equal to negative 20, and c equal to negative 17. Okay, this problem is going to pop up on an exam. You need to make sure that you know how to work this problem. Okay, so you've got to know how to work this problem, all right? And then not only that, you need to be able to explain what your answer means in the context of the problem. Okay, so using this projectile motion formula, we're calculating when the ball will be 7 feet above the ground. Okay, and we're going to use a quadratic formula to solve. All right, so this quadratic formula, so x equals negative b plus or minus square root b squared minus 4ac over 2a. So this is negative 20 plus or minus square root of negative 20 squared minus 4 times a times c all over 2 times 4.9. And when I type that in my calculator, you're going to get approximately negative 0.7. Uh-oh. I used this wrong. This isn't x, this is t here. So t here, because t is the variable. Okay. So negative 0.722, or t is roughly T is roughly 4.804. Okay? So which answer makes sense? Can I be negative 0.72 seconds? Is that the time that it's 7 meters high? Or is it after 4.8 seconds that the ball travels to this point right here? Well, since we haven't invented time travel yet, I guess we're going to have to go with this positive time interval here. Okay, so your answer, all right, so you get these two right here, but then you conclude that this one does not make sense, okay, since time is t greater than or equal to 0. We don't have time travel, no time travel, right? So my only answer, only logical answer is 4.804 seconds. Okay? So that's the only logical answer right there. All right? So that helps us out there. Now, say instead of us throwing the ball, on Earth, and our gravity here is 9.8 meters per second squared. Say instead of doing that, we threw the ball on Pluto, okay? And the gravity there, all right, the force of the gravity there is a little bit more. Well, how would that affect the time, or actually a little bit less? And how would that affect the time it takes the ball to land? Well, if you think about it, okay, I don't know if you've thought too much about the moon. Okay, so like the moon. Oh, look at this. Here we go. Right? So you don't typically fall on the moon like you would on Earth, right? So if I was going to throw a ball on Earth and I was going to throw it over here, okay, maybe it takes 4.8 seconds to get to this point right here, right? Because that ball travels just like this, right? Now, once again, I drew my guy without a head, right? But on the moon, when I throw something up in the air, it doesn't travel quite as quickly as this ball does here. Maybe it goes, right? So it spends more time in the air. So it spends more time in the air. Okay? So it takes longer for it to come back down. Since the gravity is less, okay, so since we have less gravity, right, that's going to cause the ball or the rock or whatever it is to float in the air longer. Okay, so if you thought about it, if you change that G, okay, that G mathematically, maybe on another planet, that G is like 2 meters per second squared, right? So what would that do to my equation mathematically? That would turn this equation, this would turn into a 2. And so now all of a sudden my equation goes from this right here, okay, where it was the 9.8 meters per second squared, it becomes, let's see, I guess it becomes t squared. 1 times t squared minus 20t minus 17 equal to 0. And so if we look at this, Okay, so let's graph these, see what we get. All right, so I'm gonna graph both of these. So I've got negative 4.9 x squared, okay, plus 20x, then plus 17. And my other one would be negative x squared, and then plus 20x plus 17. And so the black one is the one on the moon, and the oh, can I zoom out? Come on, let's zoom out. Can you not zoom out any? What is going on here? What in the world? Let's try this. Zoom out. It says I can pinch it and make it smaller. Well, it's not going smaller. I can zoom in, but I can't zoom out. What if I turned it like this? Does that help any? No, it does not. Why is it not? Oh well. Okay, I'm gonna have to draw it. Okay. So this curve right here looks like this. So this was that negative 0.7, and this was the this was the 4.8. That was 7 meters off the ground, right? And then this curve, okay, if I look at my graph here, okay, I think it was the black one, yeah. So the black one looked like this. All right, so you just can't see it on the other side. So at this time right here, the 4.8, we are way higher up. Okay, my height up is much higher than 7. Okay, so for me to get out to 7 meters, it's going to take a lot longer time, maybe 20 seconds. I don't know. We'd have to do the math, right? So that's the idea there. The lower that gravity, right, the longer it takes for that ball to come back down once you throw it up into the air. Okay, the stronger the gravity, the quicker the ball falls down. Okay, so hopefully this helped you out in your little application of throwing balls or rocks.